Who we got here? Usual candidates. Can you hear me?
Yeah.
Good. For some reason, I don't have a full screen, but I don't know why.
Check the screen sharing on your iPad.
Ah, yeah, well, it just went off. Yeah. Can you see this? No, you just see a blank screen?
Screen with your name.
Yeah. So what did I do wrong? Screen share.
You have to use the screen share on the iPad.
Yeah, well, I did that, I think.
You had it earlier. You did
Yeah,
earlier.
I had it earlier. Start broadcast. Let's try that.
There you go.
Okay. All right. Okay. We're good?
Yeah.
All right. All right. So today I want to, well, this week, 2 lectures, I want to give an outline of how you finish the argument. So let me just set up where we are. So now we're assuming that W is a product. Whereas we define a space, I think we defined it last time, FIQ. These are ordered Morse functions. I want to get rid of this. Okay. All right. Ordered Morse functions with exactly Q critical points of index I and Q of index I plus 1 and no others. Okay, so let's just talk for a second about that. This is a non-trivially stratified space. It's not just the top strata. Usually we talk about excellent Morse functions, which are ordered and have distinct critical values. Here, we're just requiring them to be ordered, but they can have critical values in common. So an ordered Morse function has some structure like this. It has critical points, so it's a Morse function, and it has these are the critical levels, and it's allowed to have multiple critical points at the various critical levels. So that would be a typical graphic for the Morse function here. The total number of the critical points is 2q, I of index q, and q of index I and q of index I plus 1. And let's see if I did this correctly, 2, 4, 5, 6. So I might have this. These are of index I plus 1, and these are of index I. So all the critical points of index I plus 1 occur above all the critical points of index I, but the ones index I plus 1 can have common critical values, and likewise for index I. Okay. Now we have to allow the birth-death singularities. So this is the component of births and deaths. Those are the first stratum in F with an alpha label, meaning that it's a birth or a death, that connects FIQ to FIQ plus 1. So in other words, you on one side, you'll have a situation like this with Q critical points of index I plus 1 and Q of index I, and then you'll have a path that starts there and at some point in the path produces a, oops, I did it the wrong way, produces a birth sandwiched in between the critical points of index I plus 1 and those of index I, so that you're adding one more critical point of index I plus 1 and one more of index I. It, of course, will be the bottom critical point of index I plus 1, at least for a while, and the top critical point of index I. Though as the path goes along, it may cross with some of these others, and likewise down here. So you get a graphic like that, this being the intermediate level here, not a critical level, not a critical level. Okay, and then we let Fi be the union over all Q of FIQ and FIQ alpha. Let's put a 1 here. Well, maybe I shouldn't put a 1. Okay, so it's all graphics, well, all ordered. So these are ordered functions with only birth and death. Okay. But let me just repeat what I said a minute ago in a little more detail. This space is stratified. So it's not just the top stratum. Those would be the excellent Morse functions. So FIQ0 would be excellent Morse functions, which are ordered with Q critical points of index I and Q of index I plus 1. So the difference between the general point in FIQ and the things in the top stratum of FIQ is you are no longer allowed to have multiplicities on the critical levels. So the critical values will be distinct. So these things will look like, have critical structure like this, where this is the division between I plus 1 and I. Okay. So we can see at least locally what this stratification looks like. And it's a very simple stratification locally. And let's just start with the simplest codimension 1 stratum. So that would be where you have one critical level. It doesn't really matter where it is, but let's take it to be the top one. And then all the other critical points are critical values are simple. Okay. So this is, of course, the codimension 1 stratum. And what you can do is you can move these two critical values relative to each other. So the two critical values actually give you a local function to the reals, which is the difference of the critical values. Say pick one of them and call it the first critical value for the first one minus the critical value for the second one, and the origin is the singularity. And there's a natural action of the symmetric group on two letters on this set of critical points. And what it does is it simply, on this copy of R, it flips the two values. So it has a single, it gives you a stratification of the real line where this the generic stratum is where x1 is different from x2, and there are two components of that. Well, I guess two components. And then the singular stratum is where x1 equals x2. More generally, if you had a collection of A critical points all at the same level, our picture would be, well, I should have said here, the map to R is really the critical, a pair of critical values, F of C1 and F of C2. But the only thing that matters for the structure of the stratification is the difference of these two. The absolute value where it is up and down is irrelevant. So here I have a natural map to RA, which is just the A critical values of these points. And then we have a natural action of the symmetric group, just permuting the coordinates of RA, natural permutation action, which corresponds to, so if these are the values of the A critical points near this configuration, if you decide to reorder them by some element of the symmetric group, you will just reorder the values in the same way. And the stratification then is given by this action. So for any subset J in 1 up to A minus 1, the stratum indexed by J will simply be the points in Rn, Ra, where xi equals xi plus 1 for all I in J. Okay. So for example, if you were interested in this configuration, okay, then well, how many points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're in R10, we have x1 up to x10. And J, well, the first point and the second point have the same index. So 1 is in J, 2 is in J, 3 is not in J because 3 and 4 have different critical values. 4 is not in J, 5 is in J, 6 is not in J, but 7, 8, and 9 are in J. So that's what J is. Okay. Just records, you order the critical points in a weakly descending way, and you just record which critical point has the same critical value as its successor. So in fact, it's natural to write J as a collection of intervals, 1, 2, that corresponds to 3 critical points. 3 critical points. 5, which corresponds to this doublet. and then 7, 8, 9, which corresponds to this quadruplet. So the order of each one of these intervals is one less than the number of critical points at that critical level. And so what these are is these are the maximal intervals of J, intervals in the integers. So you notice the break between every one of them and the next skips at least one integer. So here you skip only one integer because you have only one singleton, or because these are adjacent. Here you skip two integers because you go from here to here. So the local structure of the stratification, each of these intervals corresponds to, for example, that one corresponds to an R of dimension, the length of that interval plus 1 with an action of the symmetric group, just permuting the variables. And the stratification is the stratification you see of the simplex delta length of J embedded in the standard way in our length of Ji plus 1. You know, the standard way we embed the simplex with the convex hull of the unit vectors. The symmetric group then acts, sigma of the length of this interval plus 1 acts on this Euclidean space permuting the coordinates. It clearly acts, these stabilizes the simplex, so you get an action on the simplex. And the stratification is a neighborhood of the barycenter, which of course is left invariant by this action, cross R1 with a trivial stratification. So let me just work out in the two cases that the three cases that we'll need the most. If J is simply 1, 2, is simply 1, so that corresponds to a pair of critical points and then all the others separate. We have this action of the symmetric group on two letters on R2, and then just cross everything else is trivial. So let me just concentrate on this. And it looks like the action on the simplex flipping along the central point cross R. So this is the nature of the stratification along codimension 1. This is the codimension 1 stratum, where the two critical, it's a crossing stratum. This is where the critical points coalesce, have the same critical value. Here one is above the other, and here it's the reverse. If I had two pairs like this, then my interval J now has 1 and 3. So that's J, interval of length 1 going with this pair, and interval of length 1 going with this pair, 1, 2, which are same height, and 3, 4, which are same height, all the others different heights. And here we simply get sigma 2 cross sigma 2 acting on R2 cross R2 and then everything else is trivial. So this is just the product of this stratification with one in the other direction. So you have locally four top strata, codimension 0 strata, 1, 2, 3, 4 codimension 1 strata, and one codimension 2 stratum. This is independent crossings. So you move these two, critical points 1 and 2 past each other, or 3 and 4 past each other. And as we've seen, you can do it in either order. This is a codimension 2 stratum where 2 codimension 1 strata meet transversely. The other one is, that I want to think about, is when J is an interval of length 2. So now you have 3 critical points together. So the interesting part of the action is on delta 2. And the stratification looks like this. This is the triple point. So we have 3 codimension 1 strata meeting at this point. And now the question is, okay, so that's the stratification. So the local stratification, if J is a disjoint union of maximal intervals Ji, then the local stratification near a stratum of this type, near a, shall we call it J stratum, that is a stratum where the coincidence of the critical points is as described by this collection of intervals. Looks like, well, it's isomorphic to product over I of delta length of Ji. Well, I should write it this way. The star of the barycenter in delta, in the first barycentric subdivision, let's call it B1, of delta Ji, and then cross a Euclidean space of some dimension that I won't write down. So we've seen 3 cases of this. When the J is a single interval of length 1, you get the stratification looks like the stratification given by the barycenter in the interval, 2 codimension 0 strata and a codimension 1 strata across some Euclidean space. When it's given by J is 2 independent crossings, you get this product of that stratification with itself. And when J corresponds to a triple point, you get the first barycentric you get the neighborhood of the barycenter in the first barycentric subdivision of the triangle. And in general, you get products of barycenters in various simplices going with the various intervals, maximal intervals in J. So it's a nice combinatorial triangulation, stratification coming from a triangulation, product of triangulation to various simplices across a Euclidean space. Okay. And indeed, in some sense, since we're only worried about paths and homotopies of paths, all we ever need to completely understand is the 2 skeleton. And I've just explained to you the 2 skeleton. Because we're only allowing crossings here. There's no births or deaths in this Fi naught. So Fi only doesn't have any births or deaths. It only has crossings of critical points. And so the stratification is given by, the stratum is given by how many different critical points coalesce and where they are in the ordering. And then the stratification is given by products of barycenter, structure of the barycenters of simplices that come from these intervals. So that's all very combinatorial, but it's only a local description of what this stratification looks like. Okay, now I want to talk about the nerve of this stratification. And I'll do it completely generally, but then I'll apply it to in this particular case and other related cases. So suppose I have a stratified space, E, and I'll let E, I dot be the components. Everything's going to be locally path connected, so I'm not going to worry about that. The components of the ith stratum. So this is just components of the ith stratum. Okay, and then the vertices, I'm going to define a simplicial complex. The vertices of the simplicial complex, a set of vertices, is simply the disjoint union over I of the components of EI. And a simplex, well, it's a simplicial complex, so a simplex will be determined by vertices. So a simplex will have vertices A0, A1, AQ. This will be a Q simplex, where this less than or equal, this partial order is given by B is less than or equal to A if and only if B is in the closure of A. Okay. So let's just think about what happens in our case of a single codimension 1 stratum. So E, in this case, E dot naught is 2 points, and E dot 1 is a single point. So our simplicial complex has 3 vertices, and this vertex is connected to both the other 2 because it's in the closure of this stratum is in the closure of both this one and this one. So you have 2 edges, and that's it. These 2 strata are separated. Neither is contained in the closure of the other. Okay. So that's what we get. Right. All right, let's try the product of 2 such stratifications. So this time, I have 4, that's E naught dot. There are 4 components to the 0-dimensional stuff. There are 4 components to the codimension 1 stuff. And there's 1 component in codimension 2. Okay, now you have to join this codimension 1 stratum to these 2 codimension 0 strata because it's in their closure, but not in any of the others. Likewise here, and for this stratum, it's in the closure of these 2. And for this stratum, it's in the closure of these 2. Now, what about this guy? This guy is connected to everything because it's in the closure of every stratum. So this is what we get for the simplicial complex for the product of these 2 very simple stratifications. And notice that since the vertices are ordered, or at least partially ordered, so that every simplex has a total order, the nerve is what you call an ordered simplicial complex. So there's a partial order on the vertices that's a total order on the vertices of any simplex. Okay, if you have 2 such, usually you take the product of 2 simplicial complexes, you don't get a simplicial complex, you get a cell complex. But if both simplicial complexes are ordered in this sense, then the product is naturally triangulated as an ordered simplicial complex. And this gives you the usual decomposition for, say, the product of a simplex with the interval that you use to make homotopies. In this case, it gives exactly this product. So if I took the naive product of these two CW complexes, a simplicial complex like this and simplicial complex like that, I would get this thing, which is a cell complex, not a simplicial complex. It's the naive CW product. But now because both sets of vertices are ordered, there's an induced order on the pairs of vertices. In usual order, one pair is less than the other if each one is less than or equal. So this vertex is now less than this one because this corresponds to this guy, and this corresponds to, anyway, see it. So you have to add in all these edges. So this is naturally a simplicial complex whose underlying, well, which triangulates the naive product of the cell complexes. That's what happens here. Okay. Now, what does this nerve look like? Well, if you have a simplicial complex, so let's let X be a simplicial complex, then the nerve of X, well, I'm taking now the stratification, the simplicial complex stratification, namely the strata are the open, well, components of strata are the open simplices of all dimensions. Okay. So for example, if I have the barycentric subdivision of the triangle, I would have 1, 2, 3, 4, 5, 6 codimension 0 strata. 1, 2, 3, 4, 5, 6, forget the boundary. 6 codimension 1 strata and 1 codimension 2 stratum. Those are the open simplices I see. And then these simplices are ordered because you associate to each simplex its codimension. So these are 0, these are 1, and this is 2. And then the nerve is simply the first barycentric subdivision. Well, the vertices of the nerve are the simplices, and if you associate to each simplex, if you take the vertex associated to each simplex and you map it to the barycenter of that simplex, you can extend linearly. So you have a piecewise linear isomorphism from the nerve to the first barycentric subdivision of X that sends an open simplex sigma to the barycenter of sigma, and then extend linearly. Okay. So now back to our stratifications. Well, this is exactly, so for the simplex of dimension 1, we had that, and then our nerve looks like the first barycentric subdivision, well, neighborhood, the star of the barycenter in the first barycentric subdivision. For the 2 simplex, I get something interesting. Let's change color, and blue will be fine. Now I have to take the barycentric subdivision of this. Okay. What did I forget? I'm sorry. Get myself confused here. First barycentric subdivision. Yeah, I see. goes from here to here and there to there. Okay. All right. And what we're interested in is the star of the barycenter. Okay. So the star of the barycenter in the second barycentric subdivision of the 2 simplex, this is a neighborhood transverse to a codimension 2 stratum where 3 critical values are equal. Okay. So we saw the stratification was a neighborhood of the star of the barycenter in the first barycentric subdivision. That's what the stratification looked like. It's a simplicial stratification. So the nerve of that stratification is identified with the barycenter, which becomes in the barycenter of the barycenter, the second barycentric subdivision. So this is what the structure of this nerve transverse to a codimension 2 stratum looks like, or the neighborhood of the point represented by the codimension 2 stratum. Okay, so a codimension, this codimension 2 stratum as a neighborhood isomorphic to this star. And the codimension 2 stratum corresponding to 2 pairs of critical points colliding would be this one. That would be its neighborhood. Okay. And codimension 1 stratum would give you that. So we have very good hold on what locally this stratification looks like, but we don't understand it globally because as you move around, how many strata do you get and so on. Okay. But what we're interested in is this space. This is the crucial space we have to study. Phi I Q. It's the nerve of the stratification of F I Q. So these Morse functions with Q critical points of index I, Q critical points of index I plus 1, no bursts or deaths, just Morse functions. That space is stratified by the coincidence of the critical values, as I've been talking about, that locally is a nice stratification based on these barycentric subdivisions, second barycentric subdivisions of the simplices. So that's, for example, every every two face, I can say it that way. Well, I don't want to say that. Okay. So this is what we have to understand. We have to understand how you can interchange these critical points when there are only 2 of them, what all the possible interchanges are. And particular importance in the stratification is certain of its vertices. So suppose we have an excellent Morse function in this space. So the components of the excellent Morse functions are vertices in this space, vertices that come from simplices of codimension 0, with special vertices, vertices in the space. So I'll say that one of these vertices, one of these components, is homologically trivial. I'm going to say it in terms of F, but it's completely clear that it depends only on the component of F naught that contains F. So these critical points are ordered. There's C1 I plus 1, C2 I plus 1, down to CQ I plus 1, ordered by height of the critical, well, ordered by the critical value, decreasing from 1 to Q. This is the separation level. And then I look at critical points of index I and I reverse the order. Call this CQI, CQ minus 1I, on down to C1I. So anytime you have an excellent Morse function in this space, the critical points will look like that. Homologically trivial says that in order you can cancel this pair, and then once you've done that, you can cancel the next pair, and so on, all the way up the ladder. And it's a homological condition, at least in high dimensions, by Smail's theorem. But so we have what I'll call H, the homology of Wm plus, comma M. So this is going to be an intermediate level M, and this is W plus, it's part of W above M. This will be W minus, its top, minus M, its top is M, its bottom is V. Okay, so we can go by the boundary map to HI of M, and then we can include into HI of W minus M, and then we can go to HI of W minus M mod V. And this is the free abelian group generated by the C1I up to CQI, the critical points of index I. This is the free abelian group generated by C1Q plus 1, I plus 1, CQ I plus 1. So these are both free abelian groups of rank Q, and the boundary map, of course, is an isomorphism. That's the statement that W is an H cobordism. It doesn't have any homology. Okay, so that's true in general. F is homologically trivial means that boundary of C1, CQ I plus 1 equals plus or minus CQI. So the bottom critical point of index I plus 1 homologically cancels the top critical point of index I. Boundary of C I plus 1 Q minus 1 equals plus or minus C I Q minus 1 modulo the previous C I Q. So that says the boundary of the next one up, well, it's plus or minus this one, maybe plus some multiple of that one. But what it means is once you kill these two by a death, which you can do because of the homological condition, these two will now, those are gone, and then these two will kill each other, and you continue in this way. Boundary of CI plus 1 Q minus R is plus or minus CQ minus RI modulo the span of CIQ up to CQ minus R plus 1. Okay. So in high dimensions, well, sorry, if the usual hypotheses, if n is at least 6, v is simply connected, and I is between 2 and n minus 3, homologically primitive. Is that what I call it? I don't think that's what I called it. Homologically trivial. Homologically trivial means we can cancel all critical points with Q deaths and no crossings. So we start off, we kill the bottom critical, we have the bottom critical point of index I plus 1 annihilate the top critical point of index I. So if I think about my diagram, I have my path, I'm going to have these things of index I plus 1, these things of index I. The bottom one here cancels the top one here. Diagram continues. Those are now gone, and the homological condition between these two is satisfied because you've gotten rid of the indeterminacy that you had to worry about in the statement. So these two cancel each other, and then you continue, and then these two will cancel each other. So no crossings, simply a nested collection of deaths get me from the function f to a Morse function with no critical points. Okay. Conversely, if you have such a path, converse clearly is true too. If you have a path that goes from f to a function without any critical points that consists of an iterated collection of deaths but with no crossings, it looks like this, and therefore the lowest critical point here cancels the highest critical point here, and modulo that, the next one cancels the next one, and so on. Okay. All right. So that's Smale's theorem is, of course, buried in here under the high dimensions, simply connected, and I in the middle range. You can, if the things homologically cancel, then you can deform by an isotopy to make them actually geometrically cancel. Okay. And here's the theorem that we have to prove. So this is a theorem that reduces our question about connecting Morse functions without critical points by a path of Morse functions without critical points. The following. Let gamma be a good path in F1Q with endpoints in F1Q, FIQ, not 1, I naught. Okay. Excellent Morse functions. Or equivalently, we have a path gamma bar, a combinatorial path in this complex we've just been talking about. So a combinatorial path means vertex connected by a one simplex, an interval to another vertex, and so on, with endpoints coming from homologically trivial components of F naught I Q. Well, okay, I haven't said homologically. Endpoints coming from so the endpoints are required to be in the vertices that go with components of codimension 0. Then if the endpoints are homologically trivial, n greater than or equal to 6, pi 1 of the trivial, and I between 2 and n minus 4, standard sort of hypotheses, then the endpoints F naught and F1 lie in the same component of FIQ naught. So this path may be highly non-trivial, but if both endpoints are homologically trivial, then they're isomorphic. So that implies there exists a one parameter family in diffeomorphisms of W cross diffeomorphisms of I. G of 0 is the identity, so that's the G of 1 acting on F naught is F1. So F naught and F1 are connected by a path of good Morse functions. So your diagram may be quite complicated with lots of interchanges as you cross these codimension 1 strata, but there is another diagram connecting these two Morse functions, which is completely trivial. So you start with F naught and F1, and you have some diagram. So you have this intermediate level here, which is never crossed. You have these critical points of index I and I plus 1 doing who knows what from here to there. If these are both homologically trivial, then that implies that there exists a diagram like this connecting them. Diagram where nothing happens. They are diffeomorphic. They're in fact by a diffeomorphism isotopic to the identity. All right, so that's the main combinatorial theorem. It's about paths in this space, combinatorial paths in this space. Now it doesn't look like what we need to prove, so let me show you how this statement gives you the result that you want. So let me prove corollary if F naught and F1 are Morse functions without critical points, then F naught and F1 are connected by such. Okay. All right. So we start with F naught and F1, and they have no critical points. The graphic is in here. I don't know what happens. So they have no critical points. So there exist paths, alpha naught, alpha 1, from F naught and F1 respectively with Q bursts. So I should say what Q is. So this diagram is a finite diagram. So it has some maximal number. As I move through the maximal number of critical points I see at any level, is, let's say Q, is the maximal number of critical points for any ft, f lambda. Okay, that's going to be Q. So now starting, say, at F1, F1 has no critical points. I can just do a succession of bursts, nothing very interesting, and get an F1 prime, and I do Q bursts, no crossings. And I do those bursts, of course, intermediate between, well, there's no intermediate. Okay. I can do the same thing for, so that's alpha 1. I can do the same thing for F naught, these bursts, and get an F naught prime. That's alpha naught. So now consider the path alpha naught inverse followed by, I didn't give this path a name, gamma, the path from F naught to F1, followed by gamma, followed by alpha 1. So I've done something sort of silly. I have a path with a graphic that I'm trying to understand, F naught to F1, which has no critical points here or here. I put in a bunch of bursts over here, get to F1 prime. And because I've turned this path around over here, I'm putting in a bunch of deaths, F1 prime. So now I have Q critical points of index I plus 1 and I here, Q critical points of index I plus 1 and I here. And in the middle, well, I drop down to 0, I increase, but I never get bigger than Q, drop down to 0, and then increase back up to Q. Okay. Well, now I want to arrange that that the bursts, the deaths, the bursts come before the deaths. Okay. Now arrange that bursts come before deaths. So the way we do that is, suppose we have, let's look at the critical, let's look at a sequence of critical values one after another. And suppose the critical values are lambda naught, lambda 1, lambda 2, and finally lambda L, where lambda naught is a death, lambda 1 up to lambda L minus 1 are crossings, and lambda L is a birth. Okay. Well, remember, these crossings in here are either between critical points of index I plus 1 and thus above the intermediate level, or between critical points of index I and therefore below the intermediate level. And therefore, by independence of singularities, I can move this birth past all of these until it occurs right after lambda naught. So move, by independence of singularities, move lambda L before lambda L minus 1, lambda L minus 2, down to lambda 1. Okay. So then you have a birth. Everything else is trivial in this region, and then a death. And then stuff happens out here. But we're in the region where births and there's unique birth and death, so now we can amalgamate or cancel the birth and death, producing something these two give me 2 that just go right across. So I've gotten rid of this pair of birth and death. So anytime I have a birth occurring before a death, I can do this operation and cancel them. adjacent birth to death. I can cancel them. So I keep doing that over and over again until no birth, no death precedes a birth. Okay. Well, at that point, I claim there are no births or deaths. I've in fact killed them all. And the reason is I start with something with Q critical points. I end with something with a Q of index I and Q of index I plus 1. I end with something of the same size. And in the inside, I never get more critical points. Right, no more critical points than I had. So when I move these deaths to cancel the bursts, they move all the way through here and they cancel. Well, what to say, if there were any bursts occur before the deaths now, but you start with Q critical points of each type, and you never get more than Q, so you can't have a birth occurring before a death. So there are no births and there are no deaths. So what's happened when
Can you decide what Q is?
Q is the number of critical points of index I plus 1, which is also the number of index I.
Mm-hmm. In the
Q
very center.
critical. Sorry?
In the very center, right? Because you started with something without critical point.
Well, yeah, there's no critical points here or here. And then I have births and deaths here.
So somewhere in the middle, in generic middle, you have
you know, I could have fewer than Q, it wouldn't matter, but let's say I have exactly Q. Mm-hmm. So I just want to make sure I have as many here and here as I do through the path. Mm-hmm. Okay. Okay. So we end up with no births or deaths. That means we end up, when I go from this F1 prime, so I've deformed this path relative to its endpoints to one that has Q critical points all the way across. Now, of course, they still may cross, but the number is constant. So this is a path then in FIQ. No births or deaths, Q critical points throughout the path, crossings among the critical points of index I plus 1 and between the critical points of index I. That's all. It's also clear that F0 prime and F1 prime are homologically trivial, in fact, primitive. And that's because I built them that way. I started with critical points, a Morse function with no critical points, and I just put in P bursts one after another and didn't do any crossings. So that exactly makes, if you look over here from this perspective, you'll see the critical points that cancel in pairs. So this is homologically trivial, same thing over there. So now I apply the theorem that says anytime you have a path between homologically trivial things, that implies F0 prime and F1 prime are in the same component of FIQ naught. So there is another path that connects F0 prime to F1 prime that just has everything going straight across. Okay. Now I reverse what I did. I put an alpha 1 sorry, yeah, alpha 1 here, and an alpha naught here, and an alpha 1 inverse here. So remember this path, I went from F naught to F naught prime by alpha naught inverse in this direction, and here by alpha 1. So now I just reverse these paths, and I see I get back to alpha naught and alpha 1. Because I've done, if you go from here to here, I'm doing the path in its inverse, so I get right back to where I started, likewise here. So now I have a diagram connecting F naught to F1, not equivalent to the original one, but a diagram that has P bursts, Q bursts, straight across 2 Q lines, and then Q nested des from F naught to F1. Well, since there's no interchanges here, you can cancel, in other words, you have a collection of birth-death pairs nested, and by uniqueness of births and deaths, you can cancel each one of these since there's no crossing, and you're left then with a path without critical points, which goes from F naught to F1. So this reduces what we're trying to prove to a question about, where did it go? About this combinatorial structure of the nerve of the stratification, which locally is a very nice stratification coming from second barycentric subdivisions of simplices, and these special components, the homologically trivial ones. It's a question about the nerve of the stratification and paths between homologically trivial components of codimension 0, those paths all being loops in this space. So the question is then, we need to show every path in every combinatorial path in this complex with endpoints in the components FIQ that are homologically trivial. Homologically trivial components is in fact a loop. Okay, so it's now a combinatorial question, but unfortunately it's about a structure, a combinatorial structure, which locally around each point is very nice, but whose global structure we don't yet understand. And what we're going to do is we shall, in the next lecture, compare this nerve of this stratification to the nerve of a stratification defined in terms of the general linear group GLQZ, invertible Q by Q matrices, lower triangular matrices, and the symmetric group, which naturally, the symmetric group acts in a natural way on GLQZ. So the lower triangular matrices correspond to the fact that when we talked about pairs canceling each other, that was really something about a lower triangular matrix. We said this pair had to cancel on the nose. This pair canceled modulo the previous pair. So that's a little, if you think about it, a little matrix of this form. The intersection number here has to be identically 1, but the intersection number here is only plus or minus 1 modulo the intersection number of this guy with this one, and so on. So you naturally begin to see triangular matrices, lower triangular matrices coming in. And of course, we have the symmetric group as we pass the various strata where critical points collide, then we have that same symmetric group action. And the way we will compare the strata, the stratifications, is through taking homology. The comparison is through taking homology, basically. So the GL and GLQZ is the automorphism group of the homology generated by the critical points of index I plus 1, also of index I. So this group is acting on both the index I and index I plus 1 homologies. And the comparison between this stratification, geometric stratification, and this algebraic stratification is through taking homology. And the theorem will say that the map is an isomorphism. At least when the dimension is at least 7, and it's slightly weaker for 6, but good enough. So in the end, we're able to reduce this geometric stratification to this purely stratification of a complex defined in GL and Q, GLQZ, using the lower triangular matrices and the symmetric group. Exactly the ingredients that come into K1. Remember that the Whitehead group equals 0 is simply the statement that the lower triangular matrices, let's call them TQ, lower triangular, with plus minus 1s down the diagonal, triangular, and the symmetric group, sigma Q, generate GLQZ. So it's a statement about the lower triangular matrices and the symmetric group that they generate. This is now a much more complicated statement about a complex that you make using these same ingredients. And it's a statement about paths or pi1 of that complex. So the result in the end is about pi1 of a complex built from these same ingredients. GLQZ, TQ, and the symmetric group. And I'll talk about that complex on Wednesday, and I'll talk about the map, and then I'll just state the fact that it's an isomorphism, or give you the slightly weaker statement in the case n equals 6. And I won't try to prove that. I'll be out of time. All right. Well, Wednesday will be the ultimate.
Thanks again.
Keep a few of you for that. All right. Well, any questions? Okay. Well, good to see all of you.
Thanks again.
Hope you're staying safe, and I'll see you on Wednesday. I'll break out the champagne when you say.
Yes.
All right. So long.